finishing up this business about solvability series. There's two more kinds of series that I wanted to introduce you to, just so you can get the definition down. One is called a lower central series. And it starts with G0, G1, cascades down, where GK plus one, this tells you how to define it, is the commutator subgroup made of commutators from G and GK. All right, so this is inductive. So to get from G to G1, well, that's just, this right here should be the commutator subgroup. Because it's just, but the next step is the commutators of this mixed with this, that gives you V2. Next one is mixed with this, so. And here's one that you've seen a couple times, the derived series. And this is the one from the homework. G is G0. This is the commutator subgroup. The next is the commutator subgroup of the commutator subgroup, the commutator subgroup, and so forth and so on. So G1 is the commutator subgroup, and inductively GK plus one is the commutator subgroup of the K one of these things. We say that G is a solvable group if at some point you hit the identity. If you keep doing this cascading down commutators. And we saw examples last time.
And also are all abelian spaces, abelian groups solvable?
Yes, any abelian group solvable.
Just
in the first step. Right? Because if you're abelian, then, and in fact, you should think about this, if the group is solvable, the step before the identity has to be an abelian group. And that's an if and only if.
Yeah, I kind of use that to help my homework as well.
So, let me give you one more definition. Let's let G be a group. A sequence of subgroups and here's the way the sequence is going to work. I'm going to call one G0, which is normal, and G1, which is normal, and G2. And let's suppose that this is a sequence of normal subgroups, this that go from one all the way up to full group. And I'm going to put another stipulation on this. Notice, let me point out a couple of things. Number one, G0 is normal in G1, G1 is normal in G2, etc. This does not mean, well, I was going to say this doesn't mean that G0 is normal in G2, but G0 is normal in G2. Why? Because it's the identity. That's right. It's normal everything. But for example, G1 might not be normal in G3. So I'm only guaranteed that it's normal the next step up. For each G K plus one, so let's suppose that I have a sequence of normal groups and every successive quotient is simple. Is called a composition series. And GK plus one on GK is a composition family. Okay. So that's just some help. So you have the sequence of normal subgroups of G where everyone's normal in the next one and the successive quotients are all simple, right? So there aren't any normal subgroups of GK plus one mod GK except for itself and the identity symbol. And what that means, of course, is when I say that this quotient is simple, that means that there's no normal subgroups that you can put in between here. Oh, yes.
Oh, the reception. GK plus one, is it a common, or is like G,
Oh,
is that G
yes.
one?
Yes,
Okay.
that's-
And it's like all of GK, or what is like?
Yeah,
the-
so what this means is this is generated by commutators like this. Where G is in G and GK. I'm sorry, so you take these special commutators, where this can be anything in G and this has to be restricted, that's subgroup. Now, here's what composition, series. Here. 8, 1, 7. And this is one of the things that motivated the big sort of push that was done for actually decades in group theory, trying to classify the finite simple groups. This is called Jordan-Holder theorem.
Oh, Holder theorem, remember Holder's inequality from a near analysis.
So here's what the Jordan-Holder theorem says. Any two composition series for a group G have the same length in composition patterns. We have same length and composition. I am not going to prove this, but this is kind of a big theorem, and I'll explain to you why this makes it important to study things like simple groups. Let me look at a couple of examples. Over there. I'm gonna get the composition series from S3. So we'll have S3. Okay, so one is normal in any subgroup of S3. Let me see, can anybody give me an example of a non-trivial subgroup of S3? Yes.
Explain what a composition space is.
What's that?
You explain what a composition space is.
Yes. This is. So it's just a sequence of subgroups. This is G1, G0 is normal, this is normal, this, and so forth, and so on. And the successive quotients have to be simple. Here's one. This is a composition series, right? Because I started with the identity, I ended up with S3. Of course, 1 is normal in this, that's automatic, and A3 is normal in S3. Also, notice that composition factors here are A3 mod 1 and S3 mod A3, which is isomorphic to C2. Everybody agree? So the length, you might say, it depends on whether you start counting at 0 or 1. I might call this the length. I could call the identity length 0. I'll call this length 2. Right, so any two composition series of S three have to have the same length, so it'll be this thing and composition factors. Let me contrast this with Z6. There's a composition series for Z6, right? I don't have to worry about normality here because any subgroup's normal. Z6 is abelian, right? Notice that the composition factors in this case, that's 2 mod 1 and Z6 mod Z2, which is isomorphic to Z3. Everybody agree with that? But this one has another composition series. Anybody see what it is? That is correct. Z3 and Z6 mod Z3 isomorphic to Z2. Notice I have two different composition series here, okay, right? Because the stuffing in the Oreo here is Z2 and over here it's Z, right? But notice the lengths of these two are the same and the composition factors are the same, only they're in different orders. Now notice the composition factors are actually the same here, right? Do I agree with that? The length is also, I know you can say it all, the length is the same as over there, the composition factors. The only difference is this one doesn't have two different composition series, right? Why can't I put a Z2 in there? Right? Why can't I see how, so here, this is isomorphic to A3. I went 1 A3 to the top. Why can't I do a group order 2 here? How come for S3 can I not put the subgroup order or a subgroup order 2? Normally, I would expect you to be able to answer this question. That is correct. Suppose I put group order 2 here. Now where do I go? Right? Because the problem is group order 2 is not, it's a maximal subgroup. It's a maximal proper subgroup. The only group that's contained, the only subgroup that's through that contains the group order 2 is either the group order 2 itself and the whole thing, but it's not normal, right? So I can't do it that way. Let me do one more example. There are many ways to do composition series for this one. The composition factors are isomorphic to in order Z2, Z3, Z2, Z3. Z2 mod 1 is Z2. Z6 mod Z2 has 3 elements. Z12 mod Z6 has 2 elements. Z36 mod Z12 has wheel. But I could get these in other orders, right? I could also do one is normal in C3, is normal in C9, it's normal in C18, normal in Z36. And of course, every subgroup of Z36 is normal because it's abelian, but of course, what I'm doing here is I'm getting simple portions, right? I can't go from Z3 straight to Z18, right? Because if I went from Z3 to Z18, what would the quotient be? Z6, and I don't know much, but Z6 is not simple, right? So that's why I have to jump here. The composition factors here, in the order that I see them, are Z3, Z3, C2, C2. Notice, same number of composition factors, and the composition factors are in fact the same up to reordering, right? This is why the study of finite groups kind of boil down to saying, hey, look, you know what, if I've got these simple groups here are the building blocks of Z36. Basically, I can think of Z36 as being built by these four blocks put together in some way. Z6 is made up of these two composition factors put together in a certain way. So is S3. It's made of the composition factors Z3 and C2 put together in a certain way, only this time it's put together as a semi-direct product, right? And so one of the big pieces of group theory is, hey, if I know what all the simple groups are, those are the puzzle pieces that make a group in general. Now, obviously, you can't just know the simple groups because both Z6 and S3 have the same puzzle pieces, but you put them together in a different way. You put these together and it's not good, right? You put the other ones together. And of course, I can give you a more complicated group where the composition factors are not abelian. All the ones in my examples, like you might have a composition factor being A5 or something like that. That's simple. Okay. Sophia, I think you should question.
I'm just, cause at first I was confused, but you're doing, the composition factors is like C6 mod C2, C12 C mod, or mod C6.
Right. C3 mod
Okay.
1.
Okay.
C9 mod C3. C18 mod C9. C36. And that's why I haven't been so.
Oh.
Right. Any other questions? Okay. Well, I am so glad that you're here today because you've been bothering me about rings all semester.
And now we're going to cover ring theory. I knew that we were going to cover it today because I looked ahead at the notes because I saw you just for fun.
That's right. So you're going to be excited that.
I'm doing it so fun. It's fun.
So let's get into the famous. Okay. What is a ring? Well, all right. Here's basically what the deal is. We have been spending a lot of time in this class on groups. And what's a group? It's a non-empty set, binary operation, a way to combine two things and get something else from the set. Right? But one of our first examples of a group was the integers, right? You add two integers, you get an integer, the negative, blah, 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 all that. But there's more than one way to combine integers. This is familiar. One of them is you can add them, which we've done. Another one is you can multiply. So the integers have two different operations. Now, you can consider multiplication in the integers sort of an extension of addition, right? I mean, 2 times 3 is adding 3 to itself twice and 2 to itself 3 times, right? But we also know of other structures where you can add and multiply, where that analogy is not quite as transparent. The real numbers. What does radical 2 times e mean? Right? You don't add e to itself a radical 2 number of times, right? One can argue that maybe you did, but that involves infinite series and such. Basically, what a ring is it's a mathematical structure with two operations, which we will always call addition and multiplication. The addition is an abelian group, period. So we've got that lit. The additive part of a ring is just an abelian group. And you've got this other magic operation on it, multiplication, right? This is similar to when you had linear algebra, you had the scalar multiplication somewhere else. This time, the multiplication is again a binary operation. So it's a way to combine two things in our ring, two elements for our abelian group so far, and get a new element. And I want these two operations to play nicely together. They got to cooperate. So let me make precise what I mean by that. And keep in mind that yes, in almost all of mathematics, a concept like this generalizes something that is nice and good in our lives. And one thing that is nice and good in our lives is the integers. And this kind of generalizes the integers in a certain sense. A ring, and for emphasis, I'll write it this way, R plus times. So you've got two binary operations. Is a non-empty set R. With two binaries. Multiplication and addition, say, that satisfy the following. Number one, R plus is a billion. Okay. Two, dot multiplication is a subset. That is to say, A dot B dot C is A dot B dot C, all A, B, C, R. And finally, here's the play nice part. Multiplication distributes over addition. That is to say, for all A, B, C, and all, A dot B plus is A dot B. But I haven't told you enough. I need to say something else. My distributive might be a little bit incomplete at this juncture. Yeah, but I'm not going to necessarily assume that. I've told you what happens when you take a sum and hit it on the left with A. I better tell you about what happens when I hit it on the right. Notice, I didn't say the multiplication was commutative, right? And if it is, this is redundant. See if you can prove that. If the multiplication is commutative, if A times B equals B times A for everything in the ring, then that's perfect. Additionally, oh my definition. If we say R is commutative, if x, y, equals y, x, for all x, y, r. Okay. Right. And we say that R has identity or with identity. R has identity if there exists an element. I'm gonna call it one sub R. And R such that one R times X times one R is X for all X. So we say that the ring is with identity if there's a magic one that multiplies everything on either side and gives you X. We say it's commutative if the order of multiplication doesn't matter. Of course, the addition is an abelian group, so the additive order doesn't matter, but if that's also true for multiplicative, we say it's commutative. So let's look at an example or two. Example. See its ring. There's one. With the standard addition and multiplication is the operation. All right. I'm gonna tell you what the field was formally later. You all probably heard this, been in linear algebra from the field, right? Can anybody tell me what sort of the difference between the black C and yellow R compared to Z? What's the structural difference about them? Well, that's true for all of them. Is there something that's different about it? Correct. Right, so if you take these three animals here, right, of course, the addition is an abelian group. And the multiplication, familiar multiplication we have here is commutative, right? They've all got the identity, one, right? But what's different here is if you take all three of these, if you chuck out zero, just throw away zero, then under multiplication, it's also an abelian group. Agreed? This is not true for the integers. If you chuck out zero in the integers, almost nothing has an inverse, right? But what are the only two integers that have inverses that are integers? One and negative one, right? Plus and minus one are the only integers that have inverses that are still in. Here's another example. Part of being a mathematician, you have to start off and be a smart aleck. Any abelian group can be considered. I don't care what the abelian group is. You can make it a ring by making a silly rule for multiplication.
Multiplication just same as addition.
That's a good idea, but it doesn't work because I think you're gonna run into distributive problems. Do something really silly. Just declare that the product of any two elements in the ring is
The identity.
right, and let me clarify. Zero. Right, the identity elements we get. It's fairly easy to see that that's a binary operation, right? Because you take any two things, it goes to zero. It's distributive in a very silly way because any product is zero, right? And 0 plus 0 is 0, so this works. This is, you can always turn any abelian group into a ring by endowing the zero multiplication on it. Very slowly. This doesn't tell you a lot, it's very boring, but it's actually, I have seen talks where, I saw a talk one time where this person was trying to prove something in ring theory and reduced it to the case of an abelian group with zero multiplication and concluded his talk to say, now it's the group theorist's problem, right? So anyway, you can do this and it's silly, but there it is. So in other words, now I can have a finite ring just by taking a finite abelian group and endowing its multiplication. Let me ask you this, can anybody think of a finite ring? A finite ring that does not have zero multiplication, that has some influence. Right. Let me turn it. But here, the difference is we've gone over seeing quite a bit as a finite abelian group. Now, in the ring sense, what happens is the multiplication is also mod n, right? So, that's a good example here. Here's another example.
Then CP is, I can see.
That is correct. If n equals p, then this is field.
You have to specify, because you just say it's a finite ring, don't, wouldn't you have to specify what your multiplication?
Right,
is?
modulo n, right? So, K1 bar, times K2 bar, is K1, K2 bar. That is to say, to multiply 5 bar times 6 bar, multiply 5 and 6, which is 30, and then do that, in other words, reduce it. Okay, here's another example. This is probably familiar. These are all polynomials of any degree, with coefficients in the integer. What happens if I take two polynomials with coefficients and the integers and I add them up? What do I get? Another polynomial, all of whose coefficients are integers. Great. This is an abelian group. The identity of this is just the zero polynomial. The polynomial is all zeros. Right? The additive inverse of this, just change the sign on all the coefficients, right? Got that. And you all probably have enough experience now in doing mathy things. What happens if you multiply two polynomials that have integer coefficients? What do you get? Another polynomial with integer coefficients. This is actually, and the distributive property plays well here. So this is a good example of the ring. And in fact, it's not just C. You can actually do this. This is called the ring of formal power series. Now, don't worry about the calculus. It's the analysts that made the mistake of trying to plug stuff into this. Algebraists don't care about plugging stuff into this. We just consider it sort of an infinite symbol, right? It's just infinitely many power series. And how do you add power series? Turn by turn. How do you multiply them? It's like polynomials. It's just you never quit, right? So this ring right here, this is also a ring. And in fact, I'll go you one step further. If I walk up to you on the street and give you a ring, then you can construct its polynomial or its power series ring just by letting whatever that ring is, that be its coefficients. You might see how that works. here's, another example. This is actually sort of a calculus example in certain sense. Probably didn't know this when you were taking type one, but at some point you proved that the continuous functions form a ring. Because, do y'all remember this from calculus? What's one of the things they tell you? Even if they don't prove it, and I'm pretty sure they usually don't prove it, but even if they don't, they probably tell you what happens when you add two continuous functions. What do you get? A continuous function. What happens if you change the sign of a continuous function? You get a continuous function. Zero is a continuous function. These things form an abelian group. Continuous function. And there's another theorem that you apply in calculus. What happens when you multiply two continuous functions? You get a continuous function. Okay? So the continuous functions, this forms a ring. This one is commutative, right? Because the way we multiply and add functions is just pointwise. That is to say, f plus g evaluated at x is just, you just add up the ordinates of f and g at x. And f times g of x is f of x, g of x. With this rule, this is pointwise multiplication. With this rule right here, this is a commutative ring. Because multiplying f of x and g of x doesn't matter which one you do that in. This also has identity. The identity function is the function that just takes everything to one. Right? And that's the multiple identity. Yes.
I was wondering, is the polynomial rings and, are those technically also vector spaces?
Over what? That's the question. You gotta ask the field. And Z of X, you've got problems here because Z is, it's not field. So this is a commutative ring with identity. Yes.
So to clarify, if we say that a ring has an identity, then talking about the identity of the multiplication.
That is correct. It's always got an additive identity because I assume it's an abelian group. So we've got that coming out of the gate.
So then, but if somebody says, like, somebody walks up to you on the street and says, okay, here's a ring, what's the identity? Then they're talking about the multiplicative one. They're not talking about that one. Because
That
otherwise
is
they would
correct.
say,
That is correct.
what's the additive group's identity?
Right. They'll say, if they ask you what's the identity of this ring, they'll probably have to tell you what the multiplication is first, and then they say, what's the identity? They're talking about the multiplication identity. Can you give me an example of a ring that doesn't have identity? Take the ring of all even integers, right? That's certainly an abelian group. And certainly it's the case, isn't it? When I multiply two even integers, I get an even integer, right? So no problem there. It's distributive because this is, I mean, actually, this is part of the multiplication in the integers, and we know all multiplication distributes over addition in the ordinary integers, so that's here. But there is no identity. Right? There's nothing that you can multiply by everything in the things alone. I mean, if you multiply everything in here by two, it doesn't leave two alone, right? You know what I'm saying? So this is an example of a ring without identity. Can you give me an example of a ring with identity that's not commutative? No, problem is you're too specific. So,
Yes, no.
no, that's too specific. How about,
The matrix.
there you go. Example. Uh, How about the set of 2x2 real matrices? Now, he told me at first he said GL, then he said SL, right? What was the problem with that example?
Here. Under-
No, they are closed under multiplication. It's not closed under addition. Because if you, so for example, if you're demanding that your determinant is one or is non-zero, you got a problem. Because in that ring, you would have to have the identity matrix, 1, 0, 0, 1. In that ring, you would also have to have negative the identity matrix, negative 1, 0, 0, 1. When you add those two together, you get the zero matrix, which no longer has a non-zero determinant, right? This is certainly a Boolean group, right? Because adding matrices, the order doesn't matter at all, right? You're just adding them back up. But we do know from experience that the order of multiplication does matter. This one right here, I guess, is 5, 4, 2, 4. I guess. And this is already wrong. 6, 40, 2. Notice how I made those matrices up very quickly without checking first, right? I would have to be about the unluckiest person that's ever lived to make up for kind of random, 2 random matrices like that in half. Right, as long as they're not diagonal or something like that. They're not in shape. So the order here does matter. Yes.
House two doesn't have identity, but it is clear, and then M2 is not clear, but has identity.
Right. What's the identity? Well, what is it?
1, 0, 0, 1.
This is the multiplicative identity of this frame. You can expand that. In fact, you can take, I don't have to have the real numbers here. You can have any other way. I can take 2x2 matrices with entries in the integers, right? And that will be a ring that's not hidden as well. Okay, so that's some examples to kind of warm us up here. Any questions? Yes.
With the polynomial ring, you keep constructing, like you could show that you do Z adjoin X, adjoin X.
I'd call it something else, but yes. You can have a polynomial ring over Z in any number of variables, whether it's finite or any cardinality you want. Right? I mean, you can have a polynomial ring over Z in uncountably many variables. That's a very, very big ring. On the other hand, for power series, once you leave the finite, you can have so you might think about this, it really want to bend your brain a little bit. In any finite number of variables, you can have a power series. So you just stick on finite equal power series, this makes sense. However, as soon as you hit infinitely many variables, so if you go power series x1, x2, x3, and you do that infinitely many times, so this is just kind of fun, I no longer know what you mean. There are at least 3 different definitions in literature of what power series and infinitely many variables mean. And it depends on how you want to define it. So. So here's one famous result. In a commutative ring, we have binomial. somehow I have this example. Yeah. We agree. R. We have. Random. And you have all seen the binomial theorem, probably, you probably first see it in, like a high school algebra class. This is stated a little bit more generally than what you probably saw back then. If X, Y to R in grade, and N is in the natural numbers, then X plus Y to the N and X and roots A. So you all seen this, correct? You might think about, how to prove this. It's not very difficult. One way to do it is induction. And there are other kind of counting ways to do it. Let me give you this final proposition, and then I'll say something about the next one. Proposition. So here's some basic stuff about rings that you probably want to know coming right out of the gate. Here, we're going to let R be a ring. No hypothesis. At this point, 0 times A equals A times 0 equals 0 for all A and R. See if we prove. This is what you would expect to happen, I think. 0 times anything is that anything. Minus AB equals A times minus B equals minus AB for all A, B, and R. 3 minus, yes, what is minus? The additive inverse, because remember it's the billiard group. Minus A minus B is AB for all A, B, and R. If one R is in R, so if it has an identity, then it's unique. And minus A equals minus 1R times A for all A and A. And there's one more property that I'll discuss next time. I'll bring this up at the beginning, because I want to take just a minute to say something about the next homework. Start on that.
A. Like, why is A
It means that it's a typo.
Oh.
It should have been R. I got. Okay. So what I have on the next homework ball is a few ring theory. Let me point out that the last problem that I have on here is actually an optional problem, just for you to work yourself. If you're interested in getting feedback on it, you can just email it to me separately. I know it's time, so you can go if you've got a class that you gotta rush off to. But for those of you who can't stay, I'll say a couple words about the homework. Okay, the first one, so I want you to show, some properties. We didn't define what nilpotent elements are yet. But a nilpotent element means that you take that element and there's a big enough power of it, it's zero. You saw this in linear algebra, probably, you took powers of matrices and you could get zero matrix. If R is commutative, show that if X and Y are nilpotent, so if the power of both X and Y is zero, then X plus Y and X times Y are nilpotent. Show if R is a unit, that is, it's an invertible element of R, and X is a nilpotent element, then U plus X is also a unit. And show that none of this is true if you remove the hypothesis commutative. So my hint to you there is if you look at matrices, you might be able to find all the counterexamples. Number two, let R be a ring. We say that the characteristic of R is n if n times R is zero for every R in R. For example, Z mod n has this problem. Show that if R has the identity, then the characteristic of R is n if and only if n times the identity is zero, and n is minimal with respect to this property. Show that if R is an integral domain, then the characteristic of R is either a positive prime or zero. Number three is kind of fun. Suppose we say that one R respectively one L is a right respectively left identity if it's an identity on the right or on the left. Give an example of a ring that has a right identity but no left identity. Once again, matrices might be built. Number three, if you've ever graded a class, and some of you will, this is called freshman's dream. You will see this with some of your students sometimes. If you have a commutative ring with one, such as the characteristic is P, where P is prime, then A plus B to the P to the n power is A to the P to the n P to the P. You actually can't get away from that under this situation, but not usually. We define a Boolean ring to be a ring such that X squared is X for all X and R. Show that any Boolean ring is commutative and has characteristic too. The last problem doesn't count because it's not for submission unless you want to email it to me. But if you have a ring that has a property that for all non-zero A and R, this is unique, and that's important, B and R, such as ABA is A, prove the following. And I would do it in this order because it builds on itself. Number one, R has no non-zero zero divisors. Number two, BAD is B. Three, R has an identity. And finally, R is division, which means that every non-zero element has numbers. Okay, questions? All right, I would encourage y'all to be in the math club today. Neil Calkins talking. And he always gives a